So again, that is an algebraic approach, but that algebraic approach was multiplying by the conjugate. Okay, in the next example, we are going to look at the limit as x approaches 4 of 1 over the square root of x minus 2, and notice that just the x is underneath the radical, and you always need to make that really clear, minus 4 over x minus 4. Okay, if we plug 4 directly in, I get 1 over 0 minus 4 over 0. Now, when you look at 1 over 0, you might just think indeterminate minus indeterminate, but really what this is saying is this is actually infinity minus infinity. And you're going to know this if you look at this graphically. The general shape of 1 over root x minus 4, or sorry, root x minus 2. So let's take a look at these graphs real quick, and these are just quick little curve sketches. Here's the point 4 right here. This graph looks like this one. And actually this graph will look remarkably similar to it. It's just going to be scaled differently. So we can see here that this vertical asymptote, gives me that 1 over 0 here, but on either side I have limits toward infinity. So that's where this 1 over 0 is saying, that limit's going toward infinity in one direction, not in both directions. And the same with this one. This is an indeterminate form as well. And of course, indeterminate means to do more work. When you get the indeterminate form of infinity minus infinity, or undefined minus undefined, usually the best way to work with that is to combine your fractions. So take your limit that you're working with and combine them into a single fraction. So this one would end up looking like the limit as x approaches 4 of x minus 4 quantity root x minus 2, should book it 2, all over root x minus 2, x minus 4. And of course this really doesn't look much better than we already had, so let's see if we can clean this up a little bit. And actually, let's see what will happen here. 4. Let's not do that one. And when we have limits of this sort, usually we like to try and combine the fractions, or we can actually look at multiplying by conjugates or factoring as well. So let's go ahead and look at this one. Limit as x approaches 4, and let's think about some of the things that we could do here. Well, first of all, I know that x minus 4 actually factors into root x minus 2 root x plus 2. And then I can look at finding a common denominator between the two fractions. So I'll actually be combining these fractions. The common denominator would be this product. This term is missing root x plus 2, so I'd multiply top and bottom by root x plus 2. This minus 4, I'm going to write that a little different. This minus 4 actually already has the common denominator, so now my overall common denominator is root x minus 2 root x plus 2. Now you cannot cancel this root x plus 2 with this one. The bottom one is a factor, the top one is a term, and you can only cancel factors. So let's look at the limit as x approaches 4. If we combine our terms in our numerator, it looks like we have root x minus 2. Whoops. Common denominator would be root x minus 2, root x plus 2. And again, I get canceling that can occur. And I'm left with the limit as x approaches 4 of 1 over the square root of x plus 2. Plugging in directly, I get 1 over the square root of 4 plus 2. Square root of 4 is 2. 2 plus 2 is 4, and I get 1/4 for my limiting value here. You can verify that using Maple as well, and you can look at it graphically on Maple and then use your trace that we looked at in class to look at that as well to see that 1/4 does seem to be a reasonable response. Let's go ahead and look at another one. Limit as theta approaches 0. Let's use a trig function. Theta approaches 0 of cosine theta minus 1 all over sine theta. Now again, it's very important that you put parentheses around the arguments of your trig functions. If you plug directly in, we get the cosine of 0 minus 1 over sine of 0. Cosine of 0 is 1. Sine of 0 is 0, so I get 0 over 0, which is indeterminate. Indeterminate means to do more work. So the more work that we can do here is multiplying by the conjugate again. Now there might be other approaches that we can take here as well. You know, the conjugate approach certainly works a lot, but we probably could work the same problem another method too. For instance, we could probably multiply top and bottom by the sign, and then we could look at an identity for sine squared in the denominator and try and simplify from there. But this one we're going to multiply by the conjugate. The conjugate of minus 1 is cosine theta plus 1, and then of course my denominator is sine theta. Now when we have just the plain old sine theta here, I have to remember to multiply it by the conjugate as well, because whatever you do to the numerator you have to do to the denominator to keep the multiplicative identity in place, and that's what the cosine theta plus 1 divided by the cosine theta plus 1 is equal to. So from here, if we actually multiply this out, I have the limit as theta approaches 0, I have cosine squared of theta minus 1. And again, always put parentheses around the arguments of your trig functions if I haven't mentioned that. Left with cosine of theta plus 1. And then I realized that, something could factor here. I could make this a little bit more simple. So now what I do is I look at this and think, okay, I know a trig identity. So I guess, first of all, let's erase this and make a couple notes. I have a trig identity that we've worked with a lot. It's sine squared theta plus cosine squared theta equals 1. Well, if I solve this for 1 minus cosine squared theta, I get sine squared theta is equal to 1 minus cosine squared theta, which is really close to what we have. If you look at this in terms of sine squared theta, I mean, we're really close. It looks like we're just off by a negative here. Sine squared theta is equal to negative quantity cosine squared theta minus 1. And all I did there was factor out this negative, and then I'd flip the negative across. Negative sine squared theta equals cosine squared theta minus 1. And that's what I want. This is the identity that I'm actually going to plug in there. Now if we wanted to, we could have got here a lot faster. From up here, if we would have just solved for subtracting the 1 across and moving the sine squared across. But again, there's more than one way to get around there. So I'm going to make that substitution. The limit as theta approaches 0, and it looks like we're left with in the numerator negative sine squared theta because of that substitution. So we have sine theta, cosine theta plus 1. And then you'll note that the sine theta in the numerator cancels with one of the sine thetas in the the sine theta in the denominator cancels with one of the sine thetas in the numerator, and I cannot forget the negative. So let's see what we're left with. The limit as theta approaches 0 of negative sine theta over cosine of theta plus 1. Plugging directly in, I have negative sine of 0 over cosine of 0 plus 1. Sine of 0 is 0, and at this point we might worry a little bit because we might say, oh no, we're going to get 0 over 0 indeterminate again. But let's plug in the denominator and see what we get. Cosine of 0 is 1. 1 plus 1 is 2. So I get 0 over 2 here, which of course is just 0. So that is an okay limit. If I had a 0 in the denominator, I would have had a problem.